Hello everyone. So today what we're going to talk about is objects that are perfectly rolling down an incline. Now there's a couple of ways to approach this. In this video we're going to use Newton's laws. In the next video we're going to use energy. So first of all, just generically consider some rolling object which is accelerating down the hill, all right, perfect rolling, like so. There it is. Notice it's rolling, right, as it goes down the hill. So let's draw an extended force diagram. Now, whenever we've done problems with objects on inclines, right, we've always taken the axes and rotated them. We've made our new x-axis parallel to the incline and our y-axis perpendicular to the incline. Notice here, because I'm drawing an extended force diagram, I'm going to put the origin at the center of mass, which is the axis of rotation. Right? That's what this thing is rotating around, is this point right here. So, what forces act on this object? Well, of course, gravity. Gravity acts down, and it acts from the center of gravity, which would be right in the center of the object. There would be a normal force. It's being supported by the hill. What direction does a normal force act? Well, remember, normal means perpendicular, so it would be perpendicular to the surfaces, and it acts from the contact point where it's being supported. So there's the normal force. This, of course, is the angle theta, right? That's the angle of inclination, because that's how much we've rotated the axes. Now, if these were the only two forces, neither of them applies a torque, right? Neither of them applies a torque because they both act through the axis of rotation. So that means there needs to be another force that provides a torque. And that force would be friction. And in particular, because it's perfect rolling, it would be static friction. Static friction would act at the contact point, and it would act to oppose the motion, right, of it. Since the attempt would be to slide down the hill, static friction will act up the hill. Notice that static friction now does provide a torque, right? And in fact, it would a torque which would cause it to angularly accelerate clockwise, which is what it does as it rolls down the hill. So here's the extended force diagram. Right? So again, one key thing to pick up here is that if the hill was frictionless, if there wasn't this force of static friction, the object couldn't roll down the hill. Right? It would just slide down the hill, right? Because there would be nothing providing a torque on it, right, which would make it rotate, right, and roll as opposed to slide. So that's just generic, right? And this is just a generic object. Let's get a little more specific. We're going to roll three different objects: a hoop, a disc, and a solid sphere that happen to have the exact same mass and the exact same radii. All right, so the same radius. And the incline is 2.4 meters long and is at an angle of 35 degrees. So, we're going to do this in parts. First thing we're going to find, using Newton's laws, is what is the acceleration of the center of mass of each object as it rolls down the incline. Now, I'm going to do this problem very generically, right? And at the very end, I'm going to put in something that will distinguish a hoop, a disc, and a sphere. Okay, but we're going to start out just doing this generically. So let's redo the diagram. There it goes, right? Accelerates down the hill. Again, we rotate our axes. Force of gravity acts straight down from the center of gravity, which would be the axis of rotation. Now, we didn't do this before because that other force diagram is more what they would want to see on an actual AP test. No components. Right? But if we draw the components of the force of gravity, there's F of gy, there's F of gx. Notice they are perpendicular to one another, right? And there's our 35-degree angle. Now, one thing before we move on here, it may appear with the way I drew the diagram that F of gx applies a torque, but it doesn't, because F of gx is really part of F of g, and F of g acts through the axis of rotation. Right? Some physics teachers will draw this here, right? They'll draw it up here so that it's a little clearer to see that it's f of gy and f of gx are acting from the axis of rotation and therefore apply no torque. I like to draw it this way so that we can do the trig. Okay, but don't think that f of gx applies a torque here. It doesn't. It's part of f of g. We get the normal force acting from the surface perpendicular. Now, this object isn't accelerating perpendicular to the incline. That's why we rotated the axes. So therefore, f of n has to balance out f of gy. And then if it's going to roll, there's got to be something providing a torque, right? So that would be the force of static friction. Again, opposing the attempted slide down the incline. Perfect rolling, so static friction. Now, how big is that static friction? Well, remember that the center of mass is going to accelerate. So the whole point is to find the acceleration of the center of mass, which means there must be a net force acting. And if you notice here, there are two forces which act parallel to the incline, f of gx and f of fs. So if the center of mass is going to accelerate down the incline, right, f of gx has got to be larger than the force of static friction, as it is in my diagram. Right. So we can write out several Newton laws equations here. Okay, we can do two equations for the forces, right? One for the forces that are perpendicular, one for the forces that are parallel. And we can write a third equation. Because this is a rolling object, it is also rotating. And hence we can write an equation for the rotational Newton's second law. So let's do that. Remember this force diagram as we go on to the next slide. So, first one we're going to do is the y-axis. Right? So the net force perpendicular to the incline has to equal ma. But of course, it's not accelerating there, right? So f of n minus f of gy has got to be 0. And so f of n has to balance f of gy. And f of gy, if we go back to the diagram here, right, would be hypotenuse f of g cosine of 35. Now, that equation's great, but it doesn't really do anything for us because we're trying to find the acceleration. So let's look at the forces that are parallel to the incline. There are two forces that are parallel to the incline, right? F of gx and F of fs, the force of static friction. In the way I drew my diagram, F of gx is pointing in the positive direction, F of fs is pointing in the negative direction, and it will accelerate in the positive direction. If I flipped this diagram around, right, if it was going this way instead of this way, right, all the signs would change. But just as long as you're consistent, you'll get to the same place, right? So this is to the right, quote unquote, right? So it's positive this way, negative that way. Notice I got rid of all of the vectors, right? No arrows left. Very important thing to do here. So this has the acceleration. And it has f of gx, which would be mg sine theta. But the problem is, it's got friction. And I didn't tell you how much friction there is. I didn't give you a coefficient of friction. And even if I gave you the coefficient of static friction, could we just throw in coefficient of static friction times the normal force here? No. Right? We actually couldn't. Why? This is very technical. But remember that static friction, the equation is actually, static friction is less than or equal to mu times the normal force, mu s times the normal force. Right? Static friction has a range of values. So the only time static friction is equal to mu s times the normal force is when it's the maximum amount of static friction. And there is no indication in the problem that we're at some special angle where that would be the maximum amount. If they wanted it to be, they'd have to tell you. Maybe something like, this is the greatest angle before it starts to slide down the hill. Right? So then that would mean, oh, the maximum static friction. But since I didn't give you mu s, you can't do that anyway. But thankfully, we have a third equation we can use. we can say that the net torque equals I alpha. Well, again, going back to the force diagram, F of n and F of g apply no torque, right? Because they are acting through the axis of rotation. So there is only one torque in this case, and that is the torque due to the force of static friction, right? That is a negative torque because it would make it rotate clockwise. It would end up angularly accelerating clockwise and speeding up. So that means the angular acceleration is also negative. And torque, which is RF sine theta, would be RF sine of 90 because if you notice in the diagram, the static friction is perpendicular to the normal force. Or I'm sorry, it's perpendicular to R, right, which is from the axis of rotation. So the force of static friction, right, is perpendicular to the lever arm, right, which would be the radius here, right, of this. So we get negative force of static friction times the radius equals negative I alpha. Be careful, kind of with the fonts I'm using, right? These are A's. That's an alpha. Now, we're kind of mixing things here. We've got linear things here and rotational things here. So let's do a little substitution and try to put it into similar terms. Well, the substitution we can use here is that the acceleration of the center of mass, right, of this perfectly rolling object is equal to the angular acceleration times the radius. Remember that? Right, that's one of the things we derived about perfect rolling. Usually we write this as ACM, right, for the acceleration of the linear acceleration of the center of mass. But, as we did yesterday on the previous video, right, we're going to leave this as just an A. So that's an A, that's an alpha. That means angular acceleration is A over R. Plug that in. Negatives cancel. Solve. Right, solve here for the force of static friction. Right, and we get the force of static friction is IA over R squared. Rotational inertia times the acceleration of the linear acceleration of the center of mass divided by the radius squared. Right, there's one R here, and then when you move this one to the other side, they multiply together. Now we can solve this system of two equations for two unknowns. Substitute that in, and we will have eliminated the force of static friction. And we will be left with things we know and the acceleration of the center of mass that we are trying to find. So we have mg sine theta minus rotational inertia times the acceleration of the center of mass over the radius squared equals mass times acceleration. So first thing I'm going to do is move this to the other side so I can gather up the accelerations that we're trying to solve for. So just add this over there. I'm going to factor out an A, right, and then divide by this term. Right, and so here we've solved for the acceleration. Now, I'm going to do something a little funky here, and you're going to see why in a moment, why I decide to do this, but it puts the equation in a simplified form for what we're going to do next. I'm going to do something weird here. I am going to multiply the top and the bottom by 1 over the mass. 1 over the mass times the top, 1 over the mass times the bottom. Right? That's okay to do because 1 over the mass over 1 over the mass is 1. So when I multiply the top by 1 over the mass, this mass will cancel. When I multiply the bottom by 1 over the mass, it'll cancel here and leave a 1, and it'll drop it down below here. Everybody okay with that? Take this top part, multiply by 1 over the mass, you get this. Take the bottom, multiply each term by 1 over the mass, you get 1 plus I over mr squared. Now, this is as far as I can take it before I get specific with the hoop, the disc, and the sphere. If this was a single problem, like let's say it was just asking me about a hoop, I might have gone way back here And when I substituted in for alpha, I might have also substituted in the rotational inertia of a hoop here and just worked things through. Okay, but I wanted to do this problem generically so that you could kind of see what was going on. There's something that's going to pop out here that's interesting. So let's remember, the rotational inertia of a hoop about a central axis is mr squared. The rotational inertia of a disk about a central axis is 1/2 mr squared. And the rotational inertia of a solid sphere about a central axis is 2/5 mr squared. You see what's going to happen? So let's plug these in one at a time. Right? There's the hoop. There's the disk. And there's the sphere. Notice H for hoop, D for disk, S for sphere. So I just plugged in their rotational inertias. And do you see what's going to happen? Yeah, the mass and the radius cancels out in each case. That means that it doesn't matter what mass and radius the hoop has, it's going to have the same acceleration. And it doesn't matter what mass and radius the disk has, any disk will have the same acceleration. And it doesn't matter what mass and radius the sphere has, any sphere will have the same acceleration down the hill. That's kind of interesting, right? Would have been a little hard to see if we would have done that a little earlier, but right, the mass and the radius cancels. So we end up with just some fractions here. So let's work through the fractions. For the hoop, we get 1 plus 1, right? So that's 1/2 g sine theta. If we plug in 9.8 and the 35-degree angle, we get an acceleration for the hoop of about 2.8 meters per second squared. And remember, this is the acceleration of the center of mass. For the disk, it's 1 plus 1/2, which is 3/2. Flip it, it's 2/3 g sine theta. Plug in 9.8 and 35 degrees, and we get 3.7 meters per second squared. Last but not least, right, the sphere, 1 plus 2/5, that's 7/5. Flip it, it's 5/7 g sine theta. Plug in 9.8 and 35 degrees, and we get 4.0 meters per second squared. So we can see here that any sphere is going to accelerate faster than any disk, which will accelerate faster than any hoop, as long as it's perfect rolling, right? So any sphere accelerates faster than any disk, accelerates faster than any hoop. Now, that's the acceleration. What I really want to know, the whole point of doing this, was I wanted to know what order they're going to reach the bottom. Now you can probably infer this, right, from what we calculated here. But let's go ahead and figure it out, all right? Let's figure out how long it's going to take them to get to the bottom of the hill. Now, since all the forces and torques are constant, the accelerations are uniform, therefore, kinematic equations. What do we know? Well, we know the initial velocity of the center of mass is 0, because it starts from rest. We know the length of the hill. It's 2.4 meters. I'm going to call that L, all right, to work symbolically, and then I'll plug in the 2.4 meters when I calculate an answer. And then we know the acceleration of the hoop, the acceleration of the disk, and the acceleration of the sphere. So kind of like we did before, I'm going to work generically, and then I'll plug these in, okay? So which kinematic equation has time, initial velocity, displacement, and acceleration? Yes, the ever-popular third. With 0 initial velocity, that term drops out. Solve for the time. It's the square root of 2L over A, right, where L is the length of the incline, how far it's going to roll. And these are the different A's. So this is the generic answer. Let's plug each one of these in. Right. Flip the 1/2 to the top, so because I don't like fractions in my fractions. If we plug in the numbers here, the length is 2.4 meters, g is 9.8, sine of 35 degrees. We get a time of about 1.31 seconds for the hoop to roll down the hill. How about the disk? Well, if we plug in the disk's acceleration, 2 over 2/3, flip that up, so that makes 6 halves, and 6 halves is 3. Plug in the numbers, 1.13 seconds. So the disk will beat a hoop. What about the sphere? 2 over 5/7 is 14/5. Plug in the numbers, and of course, the sphere is even faster. Right? So if we were to roll these 3 objects at the same time, and in class, I'll actually show you this. I'll do a little demo of this. I actually have a hoop, a disk, and a sphere that are all the same mass and radius, specially bought just for this problem. You'll see the sphere beat the disk, which will beat the hoop. Now, if I had just asked you the order that they reached the bottom, could you have figured out the answer maybe without doing all of this work? I think you could. What would you have to consider? Well, what you would have to consider would be the rotational inertias, right? The resistance to changes in motion. Notice that a hoop has the biggest rotational inertia, and it takes the longest to get down the hill. The disk is in the middle, and it's in the middle and getting to the bottom of the hill. And the sphere is the easiest to roll, and it gets down to the bottom of the hill fastest. Right? This is, of course, if the masses and the radii are all the same, although they don't end up mattering. Okay, once you've seen that, if you remember that, right, you can just kind of compare the rotational inertias. If I had asked you right here, you might not have been able to see it because you would have gone, oh, well, what if one has a different mass or a different radius, right? In this problem, I said they were the same, but what if they weren't? Well, it doesn't really matter. Again, I'll show you in class here. I might use a big hoop and a small disk, and the disk will always beat it, whether it's a small disk or a big disk, right? Because of the mass and the radius canceling. Kind of interesting how that works, right? So the end result here of this problem, and as we can see the order they get to the bottom. Now this is one way of approaching the problem using Newton's laws. There is a second way, and that's applying the law of conservation of energy, which is what we will do in the next video.